Last night, 4 astronauts climbed aboard a spacecraft that a former NASA engineer said should never carry a crew. The heat shield had already failed. On the last test flight, over 100 chunks of material ripped off during re-entry. Deep gouges, holes, damage so bad that NASA hid the photographs for over a year. When a heat shield expert who flew the first shuttle mission after the Columbia disaster finally saw the pictures, he went public. He told reporters his answer was no, do not fly people on this machine. He said NASA was repeating the exact same mistakes that killed the crews of Challenger and Columbia. Schedule pressure overriding safety. Descent silenced. Models replacing real tests. NASA flew it anyway. Last night at 6:35 in the evening, the most powerful rocket ever to carry humans lit its engines at Kennedy Space Center. 8.8 million pounds of thrust. 4 people strapped inside a capsule sitting on top of a heat shield that everyone, supporters and critics alike, agrees will crack again during re-entry. The only disagreement is whether it will crack enough to kill them. Right now, those 4 astronauts are farther from Earth than any human has been in over 50 years. They are heading for the far side of the moon. They will lose all contact with home. They will break the record for the farthest any human has ever traveled from Earth. And then they will turn around and come back at 25,000 miles per hour through 5,000-degree plasma on that same heat shield. This is the story of Artemis II, and it is happening right now. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight we are going somewhere extraordinary. We are going to follow 4 human beings as they climb aboard a machine that some experts say should not be carrying a crew. A machine with a cracked heat shield. A machine powered by 8.8 million pounds of thrust. A machine that will carry them farther from Earth than any human being has ever traveled. We are going to follow them from the launch pad at Kennedy Space Center through the radiation belts that surround our planet and out into the void between Earth and the Moon. We are going to watch them loop around the far side of the Moon, lose all contact with home, and then turn back toward Earth at 25,000 miles per hour. And we are going to be with them during the 5 minutes at the end. The 5 minutes when the temperature outside their window reaches 5,000 degrees. The 5 minutes when the heat shield that already failed once is all that stands between them and oblivion. This is the story of Artemis II, the most dangerous trip home in the history of human spaceflight, and it is happening right now. Chapter 1: The Shield That Might Kill Them. In December of 2022, NASA launched an uncrewed capsule called Orion on a test flight around the Moon. The mission was called Artemis I. It was the first flight of the most powerful rocket ever built, the Space Launch System. The capsule flew to the Moon, looped around it, and came home. NASA declared it a triumph. Press releases praised the flawless performance. Engineers celebrated. The agency moved forward with plans to put humans aboard for the next flight. What they did not tell the public was that the heat shield came back broken. When technicians at Kennedy Space Center pulled the Orion capsule from the Pacific Ocean and brought it back to the processing facility, they found something deeply troubling. The heat shield, the curved barrier of ablative material that protects the capsule from the searing heat of atmospheric re-entry, was covered in damage. Over 100 locations showed unexpected erosion. Large chunks of material had been ripped out. Deep gouges scarred the surface. 4 separation bolts had partially melted through their thermal barriers. The damage was not what the computer models had predicted. It was not what ground testing had suggested. It was something new, something no one had seen before. NASA did not release the photographs, not for over a year. The first hint of trouble came in March of 2023, when Orion program manager Howard Hugh mentioned on a call with reporters that there had been more variations across the heat shield than expected. He said the char material had ablated differently than the computer models predicted. But he did not show the pictures. He did not describe the gouges. He did not mention the bolts. It was not until May of 2024, when the NASA Office of Inspector General published its report, that the full extent of the damage became clear. The photographs were alarming. The heat shield was pockmarked with holes. Brick-sized chunks of ablative material had broken away during re-entry. The material, called avcoat, was not supposed to come off in chunks. It was designed to char and flake away smoothly, carrying heat away from the spacecraft in a controlled process. Instead, gases had become trapped inside the avcoat blocks during the mission. When the capsule hit the atmosphere at 25,000 miles per hour, and temperatures climbed toward 5,000 degrees Fahrenheit, those trapped gases expanded. The pressure built, and the material cracked and ejected in irregular pieces, leaving the heat shield scarred and compromised. The problem was rooted in a design decision made years earlier. The original Apollo heat shields used a single honeycomb matrix of roughly 320,000 individually filled hexagonal cells. It was elegant. It was proven. It worked. But for Orion, NASA chose a different approach. Instead of one continuous honeycomb, they bonded roughly 180 individual blocks of avcoat to a carbon fiber skin. No one had ever flown a segmented heat shield like this at lunar return speeds. And Orion is not a small spacecraft. It is roughly twice as heavy as the Apollo command module. Heavier spacecraft hit the atmosphere harder, the forces are greater, the temperatures are more extreme, the margins for error are thinner, and now, here is where the story becomes uncomfortable. Because after discovering the damage, NASA did not replace the heat shield for the next mission. They did not build a new one. They did not even fly another uncrewed test to validate a fix. Instead, they changed the re-entry trajectory. On Artemis I, the capsule had used what is called a skip re-entry. It dipped into the atmosphere, bounced back up like a stone skipping across water, and then plunged back in for the final descent. This skip profile created cycles of heating and cooling that allowed gases to build up inside the avcoat. For Artemis II, NASA switched to a direct re-entry. The capsule would plunge straight in, one continuous burn through the atmosphere. No skip, no cooling cycle, no time for gases to accumulate and expand. The trade-off was significant. A direct re-entry means higher G-forces on the crew. It means a steeper angle and a more intense burst of heat. But NASA argued it would eliminate the conditions that caused the cracking. The heat shield would still crack. Everyone acknowledged that. But the cracks, they believed, would be manageable, survivable. Not everyone agreed. And the most prominent voice of dissent came from a man who understood heat shields better than almost anyone alive. His name is Charles Kamada. He is a former NASA astronaut. He holds a doctorate in engineering. He served as the Director of Engineering at Johnson Space Center, and he flew aboard the Space Shuttle Discovery in 2005 on the first crewed mission after the Columbia disaster. That disaster, which killed 7 astronauts in 2003, was caused by damage to the shuttle's heat shield. Kamada had spent his career studying exactly this kind of failure. When he saw the photographs of the Artemis I heat shield, he was alarmed. When he learned that NASA planned to fly a crew on the same basic design without an unmanned validation test, he went public. He told CNN that when asked whether Artemis II was safe to fly, his answer was no. He called the heat shield deviant. He said NASA had built what he described as toy models to retroactively justify the decision to fly. He argued that the very computational tools NASA was using to analyze the problem were the same ones that had failed to predict it in the first place. And then he said something that sent a chill through the aerospace community. He compared what was happening to the institutional behavior that preceded the Challenger disaster in 1986, and the Columbia disaster in 2003. Schedule pressure, overriding safety culture. Dissenting engineering voices dismissed or marginalized. Models substituted for empirical testing. The same pattern, the same motivated reasoning. The same institutional momentum pushing toward a launch date that had already been delayed too many times. Former NASA astronaut Danny Olivas, who served on an independent review team, was more measured but no less direct. When asked whether the heat shield would crack again, he said yes, it is going to crack. The question was whether it would crack enough to kill. NASA radiation expert Steve Scotty at the Langley Research Center pointed to another uncomfortable reality. The Avcoat material changes its physical properties roughly every 20 seconds during re-entry. The models cannot fully capture a substance that is transforming in real time under 5,000-degree heat, while simultaneously being bombarded by forces that would tear apart almost anything else. The SLS program manager John Honeycutt estimated that the mission carried somewhere between a 1 in 2 and a 1 in 50 chance of failure. That is an extraordinary range. It does not reflect confidence. It reflects fundamental uncertainty. And yet, on March 12th of 2026, the Flight Readiness Review produced a unanimous go vote. The mission was cleared. The crew was informed. The rocket was rolled to the pad. And on the evening of April 1st, 2026, 4 human beings climbed aboard. The heat shield beneath them was the same basic design that had cracked apart on Artemis I. The trajectory was different. The models said it would work. The engineers who built it said it would hold. But the engineers who understood its failure modes said the models could not be trusted. And the astronauts themselves knew everything. Commander Reed Wiseman had told reporters months earlier that if they stuck to the new re-entry path, the heat shield would be safe to fly. If. That single word carried the weight of 4 lives and a $93 billion program, because the most dangerous 5 minutes of Artemis II have not happened yet. They will come at the very end, 10 days from now, when the capsule hits the atmosphere at 7 miles per second and the heat shield either holds or it does not. But the heat shield is only one of the things that could end this mission. To understand the full scope of what these 4 people are facing, you have to understand what happened last night, April 1st, 2026, when the most powerful rocket ever to carry humans left the ground. Chapter 2, 8.8 million pounds of force. For weeks, the rocket had been standing on the pad, 322 feet tall, 5.75 million pounds loaded with fuel. A tower of engineering ambition bolted to Launch Complex 39B at Kennedy Space Center in Florida, the same pad that launched Apollo 10 in 1969. The same pad that sent 3 Skylab missions into orbit. The same pad that launched the Apollo-Soyuz test project. The same pad from which 53 space shuttle missions departed, including the last flight of Challenger. The crew arrived at Kennedy on March 27th. They had entered quarantine in Houston 9 days earlier, isolating from the rest of the world so that no common cold or stomach virus could ground a mission that had already been delayed for years. On the morning of April 1st, the countdown was deep into its final hours. Ground crews at the launch pad had begun loading propellant. Over 725,000 gallons of supercooled liquid hydrogen and liquid oxygen flowed into the core stage of the Space Launch System. The hydrogen was chilled to -423 degrees Fahrenheit. The oxygen to -297. At these temperatures, the propellants are dense enough to provide maximum energy. They are also volatile enough to turn a 300-foot rocket into the largest bomb ever assembled by human hands if something goes wrong. The crew boarded the Orion spacecraft at approximately 2:30 in the afternoon Eastern Time. They rode the elevator to the top of the mobile launch tower, crossed the access arm, and entered the White Room. This is a small enclosed space at the very top of the tower where astronauts make the final transition from the world they know to the machine that will carry them away from it. Each astronaut signed the wall. It is a tradition that dates back to the Gemini program in the 1960s. A signature, a name, a mark that says, "I was here, I chose this." They climbed into their seats. Reed Wiseman, commander; Victor Glover, pilot; Christina Koch, mission specialist; Jeremy Hansen, mission specialist. 4 seats in a capsule the size of 2 minivans, strapped in, helmets on, waiting. The countdown was not without problems. A flight termination system issue briefly placed the mission in a no-go status. This is the system that would destroy the rocket if it veered off course after liftoff. If it failed, the range safety officer could not guarantee the safety of the surrounding area. Engineers scrambled. They retrieved legacy equipment from the space shuttle era to verify the system. The clock continued. The issue was resolved. Then a battery on the launch abort system reported an unusual temperature reading. Teams assessed it and determined it was an instrumentation error, not an actual hardware failure. The weather forecast improved from 80% favorable to 90%. The final poll of the launch team produced unanimous go calls from every station. The countdown entered its final minutes. At 6:35 in the evening Eastern Daylight Time on April 1st, 2026, the 4 RS-25 engines at the base of the core stage ignited. These are the same engine design that powered the space shuttle for 3 decades. Liquid hydrogen and liquid oxygen mixed in combustion chambers operating at pressures exceeding 3,000 pounds per square inch. Temperatures inside those chambers reached nearly 6,000 degrees Fahrenheit. The engines throttled to full power. 7 seconds passed. The flight computers verified that all 4 engines were performing within limits. Then the solid rocket boosters lit. The twin boosters strapped to either side of the core stage are the largest solid rocket motors ever built. For flight, each one stands 177 feet tall. Each one burns roughly 6 tons of propellant per second. Together with the 4 core engines, they produce 8.8 million pounds of thrust. That is 17% more than the Saturn V rocket that carried Apollo astronauts to the moon. It is the most powerful launch vehicle ever to carry human beings. The hold-down bolts exploded. The mobile launcher released, and 5.75 million pounds of machine began to rise from the pad on a column of fire that turned the Florida evening into daylight for miles in every direction. The sound took several seconds to reach the spectators. When it arrived, it was not a sound you heard. It was a sound you felt. A deep, rolling thunder that rattled chest cavities and shook the ground beneath their feet. Car alarms went off in parking lots miles away. The rocket climbed, slowly at first. The thrust-to-weight ratio at liftoff was close to 1.5. For every pound of weight, the engines produced roughly 1.5 pounds of force. The acceleration was not dramatic. It was steady, relentless, building. 2 minutes after liftoff, the rocket was 29 miles above the Atlantic Ocean, traveling at 3,100 miles per hour. The solid rocket boosters had burned through their propellant. Explosive bolts fired. The 2 spent casings tumbled away from the core stage, trailing wisps of residual flame. They fell toward the ocean below. The core stage engines continued to burn. 8 minutes after liftoff, the core stage engines cut off. The rocket was now at the edge of space. Main engine cut off. The core stage separated and fell away, leaving Orion and the interim cryogenic propulsion stage alone above the planet. A single engine burn from the upper stage pushed them into a low parking orbit. 49 minutes after launch, a perigee raise maneuver brought the orbit to a stable altitude. The crew was in space, but they were not done. Just under 2 hours after liftoff, the upper stage engine fired again for approximately 18 minutes. This was the apogee raise burn. It pushed the high point of their orbit to roughly 43,760 miles above Earth. That is nearly 5 times higher than the International Space Station, higher than any astronauts had flown since Apollo 17 in 1972. The solar array wings deployed. All 4 panels unfolded from the service module and locked into position, their photovoltaic cells drinking in sunlight and converting it to the electrical power that would keep Orion alive for the next 10 days. Christina Koch and Jeremy Hansen unstrapped from their seats and began testing essential life support systems: the water dispenser, the firefighting masks, the toilet. The toilet would cause its own minor drama. During checkout, the crew reported a blinking fault light. Mission Control in Houston worked with the crew to troubleshoot the issue. The problem was resolved. The toilet was restored to normal operations. It was the kind of small, unglamorous problem that real spaceflight is made of, not the cinematic version, the real one, where a $300 billion program can be complicated by a malfunctioning waste management system. Commander Wiseman described the ascent as an amazing ride. Pilot Victor Glover, who had hand-flown Orion during the proximity operations demonstration earlier in the evening, reported that the spacecraft handled very nicely. "Very precise," he said. The crew reported that they had already witnessed 2 moonrises from their high vantage point, the moon growing and shrinking in their windows as their elliptical orbit carried them in a long, slow arc around the Earth. There was one moment of tension beyond the toilet. NASA briefly lost the ability to hear responses from the crew. Telemetry data from Orion continued to flow normally. The spacecraft was healthy, but for a brief stretch, Mission Control could not hear the astronauts speak. The communications link was restored. The moment passed, but it was a reminder. Space is not forgiving. Every system matters. Every connection matters. And when you are farther from home than any human has been in half a century, even a few seconds of silence can make the room hold its breath. The crew settled in for a 4-hour nap. They would be awakened at 7 in the morning Eastern Time on April 2nd to prepare for the perigee rays burn. This burn would lift the lowest point of their orbit, shaping the trajectory in preparation for what came next. Because the launch was only the beginning. The rocket had worked. The boosters had separated. The engines had fired on time. The solar arrays had deployed. Orion was alive and healthy in high Earth orbit with 4 human beings inside. But the hardest part of the launch was not behind them. In less than 24 hours, they would have to make the most critical decision of the entire mission. Fire the engine that commits them to the moon, or abort and come home. Once that engine fires, there is no turning back. No rescue mission, no quick return. They will be committed to a 250,000-mile journey around the far side of the moon with nothing but physics and a cracked heat shield to bring them home. The crew knows this. Mission Control knows this. And tonight, as the world watches and the Orion spacecraft integrity traces its long ellipse around Earth, the 4 people inside are preparing for a burn that will send them farther from everything they have ever known than any human being in history. But before we follow them to the moon, we need to understand who they are. Not their mission patches, not their press release biographies. Who they are as people, what they left behind, and why they chose to climb aboard a machine that some of the smartest people in aerospace said should not carry a crew. Chapter 3. The 4 who volunteered. There is a moment before every crewed spaceflight that cameras rarely capture. It is the moment when the astronaut says goodbye to their family. Not at the press conference, not at the crew walkout where they wave to the crowds. Before that, in a private room, a hug that lasts a few seconds too long. A child who does not fully understand why their parent is leaving. A spouse who understands exactly what the risks are and has chosen to let them go anyway. 4 people climbed aboard Orion on the evening of April 1st, 2026. Each of them carried a lifetime of training, experience, and sacrifice. Each of them left someone behind. Reed Wiseman is the commander of Artemis II. He is from Cockeysville, Maryland. He grew up watching fighter jets fly overhead and once saw the space shuttle riding on the back of its Boeing 747 transport aircraft. That was the moment he decided he wanted to fly. He joined the United States Navy. He became a pilot. He flew the F-14 Tomcat and the F/A-18 Super Hornet in combat deployments during Operation Southern Watch, Enduring Freedom, and Iraqi Freedom. He graduated from the United States Naval Test Pilot School, one of the most selective programs in military aviation. In 2014, he spent 165 days aboard the International Space Station during Expedition 41. His crew set a record of 82 hours of research completed in a single week. He later served as NASA Chief Astronaut, the person responsible for managing the astronaut corps and making crew assignments. When they named him Commander of Artemis II, he was already one of the most experienced people in the building. He is also a single father of 4 children. He brought his family to the launch pad. He watched them wave as he walked to the rocket. The crew chose to name their spacecraft Integrity. Wiseman said the name fit everything about how they approached training, everything about what they believed in. When reporters asked him about the heat shield, he did not flinch. He said the investigators had discovered the root cause, and that was the key. He expressed confidence in the new re-entry path. But he is not a man who ignores risk. He flew combat missions. He tested experimental aircraft. He knows exactly what the odds mean, and he climbed aboard anyway. Victor Glover is the pilot. He is a captain in the United States Navy. He flew the F/A-18 Hornet, the Super Hornet, and the EA-18G Growler. He accumulated over 3,500 hours of flight time, more than 400 carrier-arrested landings, 24 combat missions. He is a graduate of the Air Command and Staff College and holds multiple advanced degrees. In 2020, he piloted the first operational SpaceX Crew Dragon flight to the International Space Station. He lived aboard the station for 168 days. He conducted 4 spacewalks. He became the first black astronaut to live aboard the ISS for a long-duration mission. When Artemis II was announced, Glover became the first person of color to travel beyond low Earth orbit in the history of the human species. Every astronaut who has ever left low Earth orbit, every Apollo crew member, every person who has ever seen the Earth as a whole sphere has been a white American man. Until now. Glover was going through a difficult period in his personal life when he received the assignment. He told reporters about the moment he broke the news to his family. "They erupted," he said. And then his voice cracked. "I am about to start crying right now," he told the press corps. "I needed that. I did not even know I needed it." The mission gave him something to hold on to, a purpose that transcended the difficulties of the moment. He told the world that we need to celebrate this moment in human history. Christina Koch is a mission specialist. She is an electrical engineer who worked at the Amundsen Scott South Pole Station, at remote research outposts in Antarctica, and at isolated stations operated by the National Oceanic and Atmospheric Administration. She is a person who sought out the most remote, harsh, and isolated environments on Earth long before she ever thought about leaving the planet entirely. She became an astronaut in 2013. In 2019, she set the record for the longest single spaceflight by a woman, 328 days aboard the International Space Station. She participated in the first all-female spacewalks. And now on Artemis II, she became the first woman to travel beyond low Earth orbit. Koch has spoken about what this means, with a mixture of humility and clarity. She asked the public to consider what it feels like to be among the people who can call the moon a destination, not just something we look at in the sky. A destination, a place we are going. She said, "It is her strong hope that Artemis II is the start of an era where every person on Earth can look at the moon and think of it that way." She is a scientist. She is an engineer. She is a person who spent years in some of the loneliest places on Earth, preparing for a loneliness that would make Antarctica feel crowded. Because when Orion passes behind the far side of the moon, the entire bulk of the moon will block all communication with Earth. For those minutes, Koch and her crewmates will be more alone than any human beings alive. Jeremy Hansen is the fourth crew member. He is a colonel in the Royal Canadian Air Force. He flew the CF-18 fighter jet. He began flying at the age of 12 with the Royal Canadian Air Cadet Squadron. He earned his glider wings at 16, his private pilot license at 17. He was hooked before he was old enough to drive. Hansen became the first Canadian ever to lead a NASA astronaut class. He became the first non-American to fly beyond low Earth orbit. And Artemis II is his first spaceflight. He is a rookie, a fighter pilot with thousands of hours of experience in some of the most demanding aircraft ever built. But he has never been to space. Not once. His first trip will take him farther from Earth than any human being in history. He is from a farm in Ontario. He is married. He has 3 children. In videos he recorded during training, he spoke about the practical realities of the mission, with the understated matter-of-factness that Canadians are famous for. He talked about stowage, about trash management, about living in what he called a campervan-sized capsule for 10 days. And then he said something that cut through the modesty. It is extraordinary as a human being to go to the far side of the moon and look back and see the Earth from the perspective of the moon. He said it simply, as if he were describing the weather. But the weight of those words is immense. A test pilot, a combat veteran, a polar scientist, a fighter pilot who has never been to space. 4 people who have spent years training for a mission that will last 10 days. 4 people who understand the risks better than anyone outside of mission control. 4 people who were briefed on the heat shield damage, on the institutional disagreements, on the 1 in 2 to 1 in 50 odds of failure, and who decided to go anyway. The crew named their spacecraft integrity. It is a word that means wholeness, soundness, the state of being undivided and unbroken. It is also a word that means adherence to moral principle. Honesty, the refusal to compromise on what matters. They chose the name because they believed it described how they trained, how they prepared, how they faced the risk. In several hours, the translunar injection burn will fire. The engine will push Orion out of Earth orbit and onto the trajectory that leads to the moon. After that burn, there is no turning back, no rescue, no quick abort. The 4 people inside will be committed to a 250,000-mile journey through the most hostile environment human beings have ever entered. But the engine burn itself is only the beginning. Because what happens between Earth and the moon is far more dangerous than most people realize. And the first threat they will face is one they cannot see, cannot feel, and cannot outrun. It is the invisible ocean of radiation that fills the space between worlds. Chapter 4. The Point of No Return. Approximately 25 hours after liftoff, on the evening of April 2nd, 2026, the crew of Artemis II faces the single most consequential moment of their mission. It is not the launch. The launch is violent but brief. It is not the lunar flyby. The flyby is spectacular but passive. It is this: a 6-minute engine burn that will determine whether they go to the moon or come home. The maneuver is called translunar injection, TLI. It is a precise and unforgiving piece of orbital mechanics. The engine on Orion's European-built service module will fire for approximately 6 minutes. During those 6 minutes, the spacecraft's velocity will increase by roughly 900 miles per hour. That does not sound like much. Orion is already traveling at tens of thousands of miles per hour in its high Earth orbit, but those 900 additional miles per hour are everything. They are the difference between circling the Earth forever and escaping its gravitational grip. The target velocity is 24,500 miles per hour. At that speed, Earth's gravity still has enough influence over the spacecraft to guarantee a free return trajectory. This is the safety net. If something goes catastrophically wrong after TLI, if the guidance system fails, If the engine cannot fire again, if a critical system dies, the moon's gravity will catch the spacecraft as it swings around the far side, bend its path, and fling it back toward Earth. No additional engine burn required. Physics alone will bring them home. This is the same concept that saved the crew of Apollo 13 in 1970. When an oxygen tank exploded on their service module halfway to the moon, the crew could not turn around. They could not fire their main engine. They were on a free return trajectory. The moon's gravity did the work. It swung them around and sent them back to Earth. They splashed down alive. Artemis II is designed to use exactly the same type of trajectory. It is not a coincidence. It is a deliberate engineering choice made because the history of spaceflight teaches that things go wrong. And when things go wrong 200,000 miles from home, you want physics on your side. But the margin is terrifyingly thin. At 24,500 miles per hour, the free return works. At 25,000 miles per hour or higher, it does not. At the higher speed, the moon would still fling Orion back in the general direction of Earth, but the spacecraft would be moving too fast. It would overshoot. It would fly wide of the planet and continue into deep space. No rescue, no recovery, no return. 4 astronauts drifting into the void between worlds. 500 miles per hour is the difference between life and death. In orbital mechanics terms, that is a rounding error. The precision required is absolute. Before the burn, the crew has spent approximately 24 hours in high Earth orbit testing Orion's systems. This is the checkout period. If something critical fails during checkout, if life support malfunctions, if navigation is compromised, if communications drop, the crew can abort. They can fire the engine to lower their orbit and return to Earth within hours. It is the last chance to call it off. One of the key activities during this checkout period was the proximity operations demonstration. The crew manually maneuvered Orion relative to the spent interim cryogenic propulsion stage. For approximately 70 minutes, pilot Victor Glover hand flew the spacecraft through a series of controlled approach and retreat maneuvers. The exercise was designed to test skills that will be essential on future missions, specifically the ability to rendezvous and dock with a lunar lander. Glover reported that Orion handled beautifully. "Very precise," he said. After the demonstration, Orion executed an automated departure burn to safely back away from the upper stage. The stage itself would later perform a disposal burn to re-enter the atmosphere over a remote region of the Pacific Ocean. Also during the separation sequence, 4 CubeSats were deployed from the Orion stage adapter. These small satellites, contributed by Argentina, South Korea, Germany, and Saudi Arabia, will perform their own scientific experiments. The Korean CubeSat contains material designed to mimic human tissue, measuring radiation exposure as it passes through the Van Allen belts. The Saudi CubeSat will measure solar X-rays and magnetic fields. Germany's experiment will study how electrical components perform in deep space. Argentina's will measure the radiation spectrum around Earth. But the CubeSats are a sideshow. The main event is the burn. The physics of the trip to the moon are counterintuitive. It is not like driving to a destination where you accelerate, cruise, and then slow down. Going to the moon is like climbing a hill. Earth's gravity is the slope. The moment TLI ends and the engine shuts off, the spacecraft begins to slow down. Every second it moves farther from Earth, the planet is pulling it backward. Orion will decelerate constantly for the next 4 days. The numbers are dramatic. At TLI, Orion is moving at 24,500 miles per hour. By the time it reaches the midpoint between Earth and the Moon, roughly 200,000 miles from Earth and 41,000 miles from the Moon, its speed has dropped enormously. The spacecraft is crawling through space. Then something remarkable happens. Lunar gravity takes over. The Moon begins pulling the spacecraft toward itself. Orion starts accelerating again. It picks up speed as it falls toward the moon, whipping around the far side at close range before the trajectory bends it back toward Earth. The entire flight path traces a figure 8 through space. Earth at one end, the moon at the other. Orion threading the needle between them, its speed rising and falling as it trades one gravitational master for another. Commander Wiseman and the crew have spent years preparing for this burn. They have rehearsed it in simulators hundreds of times. They know the procedures by heart. They know the abort options. They know the contingencies. But simulations are not reality. No simulator can perfectly replicate the sensation of knowing that in 6 minutes you will be committed to a journey from which there is no quick return. The go-no-go decision rests with mission control in Houston and the crew aboard. Orion. Both must agree. If mission controllers see anything in the telemetry that concerns them, anything at all, they can wave off the burn. If the crew reports a problem, they can wave off the burn. But if all systems are green, if the trajectory calculations are confirmed, if the weather on the return splashdown zone looks acceptable 10 days from now, then the call is made. Go for TLI. The engine fires, 6 minutes. 900 miles per hour added to Orion's velocity. The spacecraft surges forward. Earth's grip begins to loosen. The crew watches through their windows as the planet starts to shrink. There is no turning around now. They are committed. The moon is 4 days away. The return splashdown is more than a week away. And between here and there lies a gauntlet of hazards that no human being has faced in over 50 years. Radiation that can shred DNA at the molecular level. A capsule so small that 4 people will live in it for 10 days. A heat shield that has already failed once. And a stretch of absolute silence when the moon blocks every signal from home. The crew of Artemis II has just crossed the point of no return. They are heading to the moon. And the first invisible danger is already all around them. Chapter 5. The Radiation Gauntlet. There is a shield around our planet that most people never think about. It is not made of metal or glass. It is made of magnetism. Earth generates a magnetic field that extends tens of thousands of miles into space, wrapping the planet in an invisible cocoon called the magnetosphere. This field deflects the vast majority of high-energy particles that stream constantly through the solar system. Without it, life on Earth would not exist. The surface would be sterilized by radiation in a matter of years. Every human being who has ever lived has spent their entire life inside this shield. Every person on the International Space Station orbits within it. Even astronauts who fly at 400 kilometers altitude are tucked safely inside the magnetosphere, protected from the worst of what space has to offer. The crew of Artemis II is about to leave that protection behind. And once they do, they will face radiation hazards that no human being has encountered since the Apollo program ended in 1972. The first obstacle is the Van Allen belts. These are 2 enormous donut-shaped regions of trapped radiation that encircle the Earth within the magnetosphere. They were discovered in 1958 by physicist James Van Allen using data from the Explorer 1 satellite. The inner belt extends from roughly 400 miles to about 6,000 miles above the surface. It is composed primarily of high-energy protons. The outer belt stretches from roughly 8,400 miles to 36,000 miles. It is dominated by high-energy electrons. Artemis II will cross through these belts multiple times. On the way out during the orbit, raising maneuvers, and again on the return. Apollo astronauts pass through the belts quickly, spending minimal time in the highest radiation zones. But Artemis II spent extended time in high Earth orbit during the checkout phase, which meant prolonged exposure to belt radiation at levels 50 to 100 times higher than what astronauts experience on the surface of the Earth. The belts are not uniform. They have hot spots and weak points. The most notorious weak point is the South Atlantic anomaly. a region where Earth's magnetic field dips closer to the surface, allowing belt radiation to reach unusually low altitudes. Even the International Space Station passes through this anomaly, and astronauts aboard have reported seeing flashes of light when they close their eyes. Those flashes are caused by cosmic ray particles passing through their eyeballs and stimulating the retinal cells. But the Van Allen belts are just the beginning. Once Orion clears the outer belt and crosses into cislunar space, the crew leaves Earth's magnetic protection entirely. They enter a region where three distinct radiation sources converge. The first is galactic cosmic rays. These are protons and heavy nuclei that have been accelerated to near light speed by supernova explosions and other violent events across the galaxy. They arrive from every direction. They are incredibly energetic. A single galactic cosmic ray particle can carry more energy than a fast-pitched baseball concentrated into a space smaller than an atom. These particles pass through spacecraft walls as if they were not there. They pass through human tissue. They shatter DNA molecules. They create cascades of secondary particles inside the body that can cause cellular damage far from the point of initial impact. There is no practical shielding against the highest energy galactic cosmic rays. You would need meters of solid lead to stop them, and that is not something you can carry to the moon. The second source is solar energetic particles. These are protons and electrons blasted outward from the sun during solar flares and coronal mass ejections. Unlike galactic cosmic rays, which arrive steadily, solar particle events are sporadic and unpredictable. A quiet sun can erupt with a massive coronal mass ejection in a matter of hours. When it does, a wave of high-energy particles races outward through the solar system at millions of miles per hour. If a crew is caught in deep space during a major solar particle event, the radiation dose can spike dramatically. In August of 1972, between the Apollo 16 and Apollo 17 missions, the sun erupted with one of the most powerful solar storms of the 20th century. Had an Apollo crew been in transit to the moon during that storm, they would have received radiation doses that could have caused acute radiation sickness, nausea, vomiting, impaired immune function, possible death depending on the duration and intensity. The Apollo program survived by luck. The storm happened during a gap between missions. The sun is currently moving out of its solar maximum period but remains active. NOAA forecaster Sean Dahl told reporters before the launch that things are still active. It is kind of a roller coaster ride at this point. We do not know what to anticipate. Two significant solar events during the current cycle would have prompted concern for a deep space mission. NASA has taken this threat seriously. The Moon to Mars Space Weather Analysis Office provides 24-hour monitoring. Radiation expert Mary Arone described their focus as real-time space weather analysis, prioritizing solar energetic particles and events that could produce them. NASA's Perseverance rover on Mars was watching sunspots on the far side of the sun, providing advance warning of active regions before they rotated into view from Earth. It is an early warning system spanning hundreds of millions of miles. The third radiation source is the residual exposure from the Van Allen belts themselves, which the crew will pass through again on the return journey. Orion is far better shielded than the Apollo command module. Radiation sensors throughout the spacecraft provide real-time monitoring through a system called the Acute Radiation Risks Tool. Each astronaut wears personal dosimeters that track cumulative exposure. During the Artemis I uncrewed flight, mannequins wearing radiation vests showed a 40 to 60% reduction in dose to vital organs. The vests work by adding mass around the torso, providing extra shielding for the bone marrow and internal organs most vulnerable to radiation damage. The expected total dose for the Artemis II crew under normal conditions is roughly equivalent to a whole-body CT scan. That is about 5% of an astronaut's career radiation limit. Significant, but manageable, unless the sun has other plans. Perhaps the most innovative experiment aboard Artemis II is called AVATR. Before the mission, each astronaut donated blood samples. Scientists use those samples to create organ-on-a-chip devices. These are tiny chips containing miniature replicas of bone marrow cells from each individual crew member. Bone marrow is one of the tissues most sensitive to radiation damage. The chips will fly with the crew, experiencing the same radiation environment as the astronauts themselves. After splashdown, scientists will analyze how each chip responded, providing the first personalized biological data on deep space radiation exposure from beyond the Van Allen belts. Alexandra Stankovic, the founding director of the Center for Space Medicine Research at Massachusetts General Hospital, described radiation as the #1 limitation to how far we can explore in our solar system. It is the showstopper, the thing that could ground humanity's ambitions in deep space unless we learn how to manage it. Artemis II will provide more data on this question than any mission since Apollo, but the astronauts providing that data are also absorbing the radiation that makes the question urgent. For the next 8 days, the crew of Artemis II will live and work outside the magnetic shield that protects every other human being on Earth. Their bodies will be penetrated by particles born in the hearts of dying stars, and there is nothing they can do about it except trust the shielding, monitor the instruments, and hope that the sun remains quiet until they get home. But radiation is not the only challenge of living in deep space for 10 days. Because the 4 people inside Orion are not just facing invisible threats from outside the spacecraft, they are also facing the very tangible challenge of being crammed into a space the size of 2 minivans for the better part of 2 weeks. Eating, sleeping, exercising, using the bathroom, and somehow maintaining the focus and precision required to fly a spacecraft 250,000 miles from home. Chapter 6. Life in a campervan to the Moon. The habitable volume inside the Orion spacecraft is 330 cubic feet. That is roughly 60% more than the Apollo command module, which offered 210 cubic feet for 3 astronauts. Orion has to fit 4. 330 cubic feet divided by 4 people is 82.5 cubic feet each. Imagine a box roughly 4 feet on each side. Now imagine living in that box for 10 days, with 3 other people, while hurtling through the vacuum of space at thousands of miles per hour. The capsule was designed for survival, not comfort. Every cubic inch of interior space serves a purpose. The 4 launch and re-entry seats dominate the cabin during the powered phases of the mission. Once in orbit, the crew reconfigures the interior. Koch and Hansen's seats are folded and stowed. Wiseman and Glover's seatbacks remain in place, but the footpans are removed. This creates a slightly more open living area. In microgravity, the crew does not need to stand on a floor. They can use the full 3-dimensional volume of the cabin. Walls become floors. The ceiling becomes workspace. Every surface is potential real estate. Sleeping arrangements are Spartan. Wall-mounted sleeping bags, similar to the ones used on the International Space Station, are tethered to handrails inside the capsule. The crew sleeps in a synchronized 8-hour schedule, all 4 at the same time. There are no private bedrooms, no doors, no separation. Just 4 people floating in the dark in sleeping bags attached to the walls of a capsule the size of 2 minivans, while the moon grows larger in the windows. The food is entirely pre-packaged. No fresh fruit, no salads, no hot coffee brewed from beans. Everything is either dehydrated or thermostabilized, meaning heat-treated and sealed in pouches. The crew selected their menus before the mission, working with NASA food scientists to ensure nutritional balance while accommodating personal preferences. A water dispenser and a food warmer allow the crew to rehydrate meals and heat them to something approximating a pleasant temperature. Eating in microgravity is a skill. Crumbs float. Liquids form wobbling spheres. A dropped utensil does not fall. It drifts slowly across the cabin until it sticks to an air vent or lodges behind a panel. Exercise is not optional. In microgravity, muscles begin to atrophy and bones begin to lose density almost immediately. On the International Space Station, astronauts exercise for 2 hours every day to counteract these effects. On Artemis II, the crew has a more compact regimen. They use a flywheel exercise device that is smaller than a carry-on suitcase. It sounds modest, but the device is capable of providing resistance equivalent to rowing, squats, and deadlifts of up to 400 pounds. Each crew member does approximately 30 minutes of exercise nearly every day. The exercise has a secondary purpose beyond keeping the crew healthy. NASA is monitoring how the vibrations generated by 4 exercising humans affect Orion's steering systems. On the International Space Station, astronaut exercise causes measurable vibrations that propagate through the structure. The station is large enough to absorb them. Orion is not. Engineers need to know whether a vigorous squat session at 200,000 miles from Earth can disrupt the spacecraft's attitude control. They also need to know how the life support system handles the spikes in carbon dioxide and humidity that come when 4 people are breathing hard in a sealed capsule. The toilet is perhaps the most unglamorous but most essential piece of hardware aboard Orion. It is called the Universal Waste Management System. It was 3-dimensionally printed from titanium. It is 60% smaller than the toilet used on the space shuttle. Urine is collected and vented into space. Solid waste is stored in containers for return to Earth. A small door provides privacy, which is a luxury that Apollo crews never had. On Apollo missions, astronauts used plastic bags taped to their bodies. The entire crew could see. The process was described by multiple Apollo astronauts as the most unpleasant aspect of the mission. If the toilet fails, and it briefly did on the first night of the mission before being restored, backup systems are available. Foldable urinals and manual waste collection can substitute, though with significantly reduced dignity and convenience. NASA project manager Melissa McKinley described the system as an evolution of design that built on lessons from Apollo, the shuttle, and the space station. The fact that a space agency spends years designing and testing a toilet tells you everything you need to know about the gap between the cinematic version of spaceflight and the real thing. Communication with Earth is maintained through the Deep Space Network, an international array of giant radio antennae positioned in California, Spain, and Australia. The 3 stations are spaced roughly 120 degrees apart around the globe, ensuring that at least one is always in contact with any deep space mission. The crew has Wi-Fi aboard the spacecraft. They can send and receive messages. They can make video calls. They hold regular private medical conferences with flight surgeons on the ground, reporting any symptoms or concerns. The daily schedule aboard Orion is structured but not rigid. Each day has designated tasks. On day 3, the crew conducts a CPR demonstration in space, practicing emergency medical procedures in an environment where cardiac compressions require bracing against a surface because there is no gravity to push against. They also test the Deep Space Network communications link, verifying that voice and data can be reliably transmitted across the growing distance between Orion and Earth. Day 4 is dedicated to reviewing the imaging plan for the upcoming lunar flyby. The crew will have only about 3 hours during their closest approach to the Moon. Every minute of that window has to be choreographed. Which cameras, which angles, which geographic targets, which windows to use. The crew has rehearsed this plan many times on Earth and will practice it again during the coast phase. Day 5 brings emergency suit donning practice. The crew rehearses, rapidly getting into their Orion Crew Survival System spacesuits. These are the orange suits they wore during launch. In an emergency, a cabin depressurization or a fire, the suits are the last line of defense. The crew must be able to get into them quickly and correctly with their hands shaking and their hearts pounding. Also on day 5, Orion enters the lunar sphere of influence. This is the invisible boundary in space where the Moon's gravitational pull becomes stronger than Earth's. The spacecraft does not cross a physical line. The transition is gradual. But it marks a psychological milestone. The moon is no longer a destination in the distance. It is the dominant gravitational force acting on the spacecraft. Orion is falling toward it. The mundane rhythms of life aboard Orion, the meals, the sleep, the exercise, the toilet, the medical checks, are all set against this backdrop of cosmic isolation. Every hour that passes takes the crew farther from everything they know. The lag in communication grows. The Earth shrinks in the windows. The silence of space presses in from every direction. Jeremy Hansen described it simply. It is a campervan-sized capsule. That is accurate. But it is a campervan hurtling through the void between worlds with 4 people inside who are farther from help than any human beings have ever been. And on day 6, they will reach the place that makes it all worth it. The far side of the moon, Chapter 7, The Far Side. There is a side of the moon that no one on Earth has ever seen with the naked eye. Not from the surface, not from any rooftop, not from any mountaintop. The moon is tidally locked to the Earth, meaning the same hemisphere always faces our planet. The far side remains perpetually hidden. We know it is there. We have photographed it from orbit. We have mapped it with satellites, but no human eye has ever looked directly at the far side of the moon from close range since the Apollo program ended more than half a century ago. On day 6 of the Artemis II mission, approximately April 6, 2026, the crew of Orion will become the first human beings in over 53 years to see it. The approach is gradual. By day 5, the moon has grown from a bright dot in the sky to a massive presence dominating the forward windows. As Orion enters the lunar sphere of influence, the moon's gravity accelerates the spacecraft, pulling it faster and faster toward the ancient surface. The crew can see craters, individual features, ridges and valleys, and the dark, smooth plains of ancient lava flows called Maria. The spacecraft does not enter lunar orbit. Artemis II is a flyby mission. Orion will swing around the moon in a single pass, threading between the lunar surface and the void beyond. At its closest approach, the spacecraft will be approximately 4,100 miles above the surface. From that distance, the moon will appear about the size of a basketball held at arm's length. Jeff Radigan, the lead flight director for Artemis II, used that exact comparison. If you held a basketball out from your hand and looked at it, that is about how big the moon will appear in the crew's window. But the numbers do not capture what this will feel like. The crew has approximately 3 hours during the closest pass to complete their lunar observation. Objectives. They have rehearsed this window many times. The tasks include naked eye observations, photography, video recording, and identifying specific geographic targets on the surface. They will be among the first humans to see large regions of the far side up close. Apollo missions orbited near the equator, and their far side passes were often in darkness. Artemis II approaches on a different trajectory, with potential illumination of regions that have never been observed by human eyes in direct sunlight. The crew will attempt to capture a new Earthrise photograph. This is the iconic image, first captured by Apollo 8 astronaut William Anders in 1968, of the Earth rising over the lunar horizon. That photograph changed the way humanity saw itself. It showed the planet as a small, fragile sphere alone in the blackness of space. No borders visible, no nations. Just a thin blue atmosphere wrapped around a ball of rock and water. The Earthrise from Artemis II will be different from Apollo 8's in a fundamental way. The people taking the photograph will be different. For the first time in history, the eyes looking back at Earth from the vicinity of the moon will include a woman, a person of color, and a non-American. Koch, Glover, and Hansen will see what 12 white American men saw during Apollo, and they will bring perspectives that those men could not. But perhaps the most profound moment of the flyby will be the silence. As Orion passes behind the far side of the moon, the entire mass of the moon will sit between the spacecraft and the Earth. Radio waves cannot penetrate 700 miles of solid rock. All communication with mission control will cease. no voice calls, no data transmission, no telemetry. For those minutes, the 4 astronauts aboard Orion will be completely cut off from every other human being alive. During Apollo missions, the loss of signal behind the moon was a regular occurrence. The astronauts orbited the moon multiple times, losing and regaining contact on each pass, but they had been living in the context of repeated orbital passes. It was routine. On Artemis II, the loss of signal happens only once. The crew passes behind the moon, enters silence, and then emerges on the other side. The silence is singular, it is absolute. And it is, by any measure, the loneliest any human beings will ever be. Picture it. 4 people in a capsule the size of 2 minivans. Outside the windows, the ancient cratered surface of the far side of the moon, illuminated by the sun but never seen from Earth. Behind the moon, hidden by its mass, the Earth, every person they love, every sound they know, every signal that connects them to home, all of it blocked, all of it gone. For those minutes, they are entirely alone with each other and with the universe. Christina Koch spoke about this before the mission. She asked people to think about what it means to be someone who can call the moon a destination. Not something you look at, something you travel to, something you approach, something you fly past close enough to see individual boulders on its surface. And then comes the record. Artemis II will pass approximately 4,700 miles beyond the far side of the moon. When it reaches its farthest point, the crew will be approximately 252,799 miles from Earth. That is farther from home than any human being has ever been. The previous record was set by the crew of Apollo 13 in 1970. They reached 248,655 miles from Earth. The difference is about 4,144 miles. Roughly the distance from New York City to London. There is a profound irony in this record. The Apollo 13 record was set by a crew desperately trying to survive. Their oxygen tank had exploded. Their service module was crippled. They used the moon's gravity to slingshot home in a terrifying improvisation that became one of the most famous survival stories in human history. Their record distance was not an achievement. It was a consequence of disaster. The Artemis II record is different. This crew chose to go. They knew the risks. They understood the heat shield controversy. They sat through the briefings. They heard the dissenting voices. And they boarded the spacecraft and rode 8.8 million pounds of thrust into the sky because they believed the mission mattered. After the far side pass, Orion begins its return trajectory. The moon's gravity bends the flight path, slinging the spacecraft back toward Earth. The figure 8 is complete. The crew has seen what only a handful of humans have ever seen. They have been farther from home than any living thing with a heartbeat has ever traveled. And now they are heading back. But the wonder of the far side gives way to a growing tension. Because every mile that brings them closer to Earth brings them closer to the heat shield test. The 5 minutes that will determine whether the mission ends in celebration or catastrophe. The most dangerous part of the journey is not the launch. It is not the radiation. It is not the far side. It is coming home. But before we follow the crew through that fiery return, we need to step back and ask a question that has haunted the Artemis program since its inception. A question about money, about politics, about whether the most expensive machine in human history was worth building, and about the very different rocket that is waiting in the wings. Chapter 8. The $93 billion rocket. The Space Launch System was not born from a grand vision. It was born from a cancellation. In 2010, President Barack Obama cancelled the Constellation program, NASA's previous attempt to build a rocket capable of returning humans to the moon. Constellation had been running behind schedule and over budget. Its Ares rockets were plagued by technical problems. The program was bleeding money with no clear end in sight. so it was killed. But killing a NASA program is not the same as killing the jobs that depend on it. Thousands of engineers, technicians, and contractors across multiple states were employed by Constellation. Their congressional representatives were not about to let those jobs disappear. So Congress did what Congress does. It passed a law. The NASA Authorization Act of 2010 mandated that the agency build a new heavy-lift rocket using existing shuttle-era hardware. The RS-25 engines that had powered the space shuttle for 3 decades, the solid rocket boosters derived from the shuttle program, a core stage based on the shuttle external tank design. The directive was specific. Use what already exists. Keep the workforce employed. Build the rocket in the same facilities, in the same congressional districts, using the same contractors. The goal was not efficiency. The goal was continuity. Jobs in Alabama, where the Marshall Space Flight Center oversees propulsion. Jobs in Louisiana, where the Michoud Assembly Facility builds the core stages. Jobs in Florida, where Kennedy Space Center handles launch operations. Jobs in Utah, where Northrop Grumman builds the solid rocket boosters. The nickname emerged almost immediately: the Senate Launch System. It stuck because it was accurate. The SLS was designed as much by political requirements as by engineering ones. The rocket that would eventually carry humans back to the moon was shaped by the geography of congressional districts more than by the physics of spaceflight. The original projected cost for development through 2017 was roughly $18 billion. The early per-launch estimate was approximately $500 million. Those numbers now read like fantasy. By 2025, over $60 billion had been spent on the SLS and Orion programs combined. The total program cost through the early Artemis missions was approaching $93 billion. Each individual launch now costs approximately $4 billion. The White House's own 2026 budget proposal described SLS as grossly expensive and noted that it was 140% over its original budget. NASA Inspector General Paul Martin told Congress that the $4.1 billion per launch price tag struck his office as unsustainable. The core of the cost problem is the contracting structure. Boeing is the prime contractor for the SLS core stage. The contract is cost plus, meaning Boeing is reimbursed for all expenses incurred plus a guaranteed profit margin. If costs increase, the taxpayer pays the difference. Boeing does not absorb overruns. Between 2013 and 2017, a period of massive schedule delays and hundreds of millions of dollars in cost overruns, Boeing received approximately $234 million out of a possible $262 million in available award fees. They were paid nearly the maximum performance bonus during a period of objectively poor performance. Martin did not mince words in his congressional testimony. He cited poor contractor performance on Boeing's part, poor planning, poor execution, and on NASA's side, poor project management and contract oversight. The system was designed to reward spending, not results. And it performed exactly as designed. The rocket itself is entirely expendable. Every component of the SLS is destroyed during or after each launch. The solid rocket boosters fall into the ocean. The core stage is jettisoned. The upper stage is disposed of. Nothing comes back. Nothing is reused. Every mission requires building an entirely new rocket from scratch. In the history of spaceflight, this approach made sense when no alternative existed. In 2026, an alternative exists. SpaceX's Starship stands 397 feet tall. It produces 17 million pounds of thrust at liftoff, nearly double the SLS. It is designed from the ground up for full reusability. Both the Super Heavy booster and the Starship upper stage are intended to land, be refurbished, and fly again. Elon Musk has claimed that future per-launch costs could fall below $10 million. Even if the actual cost is 10 times that estimate, it would still be a fraction of what a single SLS launch costs. The comparison is uncomfortable for SLS defenders. SpaceX's Human Landing System contract for the Artemis program is $2.9 billion. Fixed price, not cost plus. SpaceX owns the hardware, NASA buys the service. If SpaceX's costs increase, SpaceX absorbs the overrun. The incentive structure is inverted. SpaceX is rewarded for efficiency. Boeing is rewarded for spending. In December of 2025, Jared Isaacman was confirmed as NASA administrator. Isaacman is a billionaire entrepreneur who personally flew to space twice on SpaceX missions, including the Polaris Dawn mission that conducted the first commercial spacewalk. He arrived at NASA with a mandate to cut costs and accelerate timelines. He moved fast. In February of 2026, Isaacman cancelled the development of the Block 1B version of SLS. He cancelled the exploration upper stage. He cancelled the Block 2 configuration. These were planned upgrades that would have increased SLS capability, but at costs of additional billions. In March, he cancelled the Lunar Gateway, a planned space station in lunar orbit that had already consumed over $3 billion in development. He declared it unnecessary. In its place, Isaacman announced plans for a permanent moon base at the lunar South Pole with a projected cost of $20 billion. The vision shifted from orbital infrastructure to surface presence. From a way station to a settlement, the Artemis program now stands at a crossroads. The SLS has proven it can fly. The April 1st launch demonstrated that the most powerful rocket ever to carry humans works. But it works at a cost that even its defenders acknowledge is not sustainable over the long term. The question is not whether SLS can do the job. It can. The question is whether the country is willing to spend $4 billion every time it wants to send a capsule to the moon, when a potentially reusable alternative is being built in South Texas. The $93 billion already spent are gone. That money bought a rocket, a spacecraft, an infrastructure, and the institutional knowledge to operate them. Whether that investment was wise or wasteful depends on what happens next. If Artemis leads to a permanent human presence on the moon, the cost may be justified by history. If the program stalls under its own financial weight, the SLS will be remembered as the most expensive monument to government contracting ever built. But the financial debate is not the only pressure bearing down on Artemis. There is another force at work, a force that has nothing to do with congressional districts or contractor fees. It is the force of competition. Because America is not the only country racing to the moon, and the other major contender has a track record of hitting its deadlines. Chapter 9: The New Space Race. The first space race was between two superpowers, and it was about prestige. The United States and the Soviet Union spent billions to prove which system, capitalism or communism, could reach the heavens first. The Soviets launched the first satellite, Sputnik, in 1957. They put the first human in space, Yuri Gagarin. In 1961, they achieved the first spacewalk. They landed the first probe on the moon. They were winning. And then America went all in. President John F. Kennedy declared that the nation would land a man on the moon before the decade was out. NASA received nearly 4.5% of the entire federal budget. In 1969, Neil Armstrong stepped onto the lunar surface. America won. And then, America quit. After Apollo 17 in 1972, no human being left low Earth orbit for over 50 years. The race was over. There was no one left to race against. Now there is. China has emerged as the most capable and most determined challenger to American dominance in space. And unlike the Soviet Union, which collapsed under the weight of its own dysfunction, China is building its space program with methodical precision, generous funding, and a track record of delivering on schedule. The milestones are striking. In 2019, China landed the Chang'e 4 probe on the far side of the moon. It was the first spacecraft from any nation to achieve a soft landing on the far side. In 2020, Chang'e 5 returned lunar samples to Earth. In 2024, Chang'e 6 returned samples from the far side of the Moon, another global first. No other country has accomplished this. The next steps are already in motion. Chang'e 7, scheduled for 2026, will land at the lunar South Pole to survey for water ice and other resources. Chang'e 8, planned for 2029, will begin construction scouting for the International Lunar Research Station. And China has pledged to land Chinese astronauts, called taikonauts, on the Moon by 2030. China does not bluff about timelines. When China says 2030, the international aerospace community takes that date seriously because China has consistently met or beaten its stated schedules. The country built and staffed its own orbital space station, Tiangong, in record time. It has launched more orbital rockets than any other nation in recent years. Its space budget has been growing steadily, while NASA's has been flatlined by congressional appropriations battles. In 2021, China and Russia announced a joint project called the International Lunar Research Station, the ILRS. This is a direct counterweight to the American-led Artemis program. The ILRS is planned in 3 phases: reconnaissance from 2021 to 2025, construction from 2026 to 2035, and utilization from 2036 onward. The partnership has attracted a coalition of nations that reads like a deliberate alternative to the Western Alliance: Pakistan, Egypt, South Africa, Venezuela, Thailand, Senegal, Turkey. The list is growing. On the American side, the Artemis Accords have been signed by 60 nations. These accords establish principles for peaceful lunar exploration, including transparency, interoperability, and the deconfliction of activities. But the accords are not without controversy. Critics argue that the safety zones they establish around lunar operations amount to de facto territorial claims, something the 1967 Outer Space Treaty was designed to prevent. China has framed the American approach as space enclosure and positioned the ILRS as a more equitable alternative aligned with international law. The strategic prize driving both programs is the same: water ice at the lunar South Pole. In 2018, NASA confirmed the presence of water ice in permanently shadowed craters at the Moon's South Pole. These craters, some of which have not seen sunlight in billions of years, contain deposits of frozen water that could transform human spaceflight. Water means drinking water for astronauts. It means breathable oxygen, which can be extracted through electrolysis. And most importantly, it means rocket fuel, hydrogen and oxygen, the same propellants that power the SLS and virtually every other chemical rocket, can be manufactured from lunar water ice. A base at the South Pole with access to water ice would be the most strategically valuable piece of real estate in the solar system. It would be a refueling station for deep space missions, a staging point for Mars, a manufacturing center for propellant that does not need to be hauled up from Earth's crushing gravity well at a cost of thousands of dollars per kilogram. Whoever controls that base controls the infrastructure of deep space exploration for the next century. Both the United States and China are targeting the same region. Both are planning bases. Both are planning to mine water ice, and they are operating under incompatible legal frameworks. The Artemis Accords establish safety zones around operations. China does not recognize those zones. If both nations establish operations in close proximity at the South Pole, the potential for interference, accidental or otherwise, is real. This is not science fiction. This is geopolitics projected onto the lunar surface. The same dynamics that drive territorial disputes on Earth, competing claims, overlapping interests, incompatible legal interpretations, mutual suspicion, will follow humanity to the Moon. The question is whether they can be managed peacefully or whether the Moon becomes yet another arena for great power competition. Canada's role in Artemis extends beyond Jeremy Hansen's presence aboard Orion. The Canadian Space Agency developed Canadarm3, a new generation robotic arm, originally intended for the Lunar Gateway. The Gateway's cancellation by Isaacman has created uncertainty about Canadarm3's future, but Canada's commitment to the Artemis partnership remains firm. The European Space Agency built Orion's service module, the critical component that provides power, propulsion, and life support. Japan, South Korea, and multiple other Artemis partners are contributing hardware, science, and expertise. The Moon race is not a solo sprint. It is coalition warfare. The parallel to the original space race is imperfect but instructive. In the 1960s, the race was about proving ideological superiority. In the 2020s, the race is about establishing infrastructure. The first space race ended with footprints and a flag. The second space race will end with bases, mines, and supply chains. The stakes are not symbolic. They are material, they are strategic, and they are permanent. For the 4 people inside Orion, the geopolitical dimensions of their mission are distant abstractions. They are not thinking about congressional budgets or competing legal frameworks or Chinese landing schedules. They are thinking about the systems they need to monitor, the procedures they need to execute, and the growing reality that they are now heading home. The Moon is behind them, the Earth is ahead, and the most dangerous part of the mission is getting closer with every passing hour. Chapter 10. The Long Coast Home. Day 7. The Moon is shrinking in the rear window. Earth is growing ahead. Orion has exited the lunar sphere of influence and is now falling back toward home, accelerating gradually as Earth's gravity reasserts its dominance over the spacecraft. The figure-8 trajectory is bending back on itself. The outbound journey is over. The return has begun. Day 7 is officially the crew's day off. But a day off in space 200,000 miles from Earth does not mean rest in any conventional sense. The crew still monitors systems. They still check communications. They still review procedures. And they carry the emotional weight of what they have just experienced. They have seen the far side of the Moon. They have been farther from home than any human being in history. They have passed through the silence behind the Moon, where no signal from Earth could reach them. Now they are heading back, and the mood aboard Orion is shifting. The wonder is giving way to something else. Not fear, exactly. Preparation. Focus. The crew knows what is waiting at the end of this coast. They know the heat shield's history. They have been briefed on every detail of the Artemis, one damage. They have studied the computer models and the dissenting opinions. They understand that the Avcoat will crack again. The question, the only question that matters, is whether it cracks enough to kill. During the coast home, the crew demonstrates Orion's radiation shielding capabilities. They test manual piloting of the spacecraft. They collect the science data that will be analyzed for years after the mission ends. Saliva samples, both wet and dry, are taken for immune system analysis. Scientists want to know whether dormant viruses are reactivated in deep space. On the International Space Station, astronauts have shown reactivation of herpes family viruses, including the viruses that cause chickenpox and shingles. The stress and radiation of spaceflight appears to suppress the immune system enough to allow dormant infections to flare. If this happens in deep space, where medical evacuation is impossible, the implications are serious. The Avatar organ-on-a-chip devices are still collecting data. The tiny chips containing replicas of each astronaut's bone marrow cells have been exposed to the same radiation environment as the crew for the entire mission. They will be among the most valuable biological samples ever returned from deep space. Scientists at multiple institutions are waiting for them. The international CubeSats deployed earlier in the mission are conducting their own experiments independently. The Korean K-RAD cube is measuring radiation using material designed to mimic human tissue. The Saudi Space Weather CubeSat is recording solar X-rays and magnetic field data. The German Tacheles experiment is studying how electrical components perform in the deep space environment. Argentina's Atenea is collecting radiation spectrum measurements. Each of these small satellites contributes a piece of the puzzle that future missions will depend on. On days 8 and 9, the tension builds visibly. The crew performs multiple return trajectory correction burns. These are small engine firings that adjust Orion's path with surgical precision. The splashdown zone in the Pacific Ocean off the coast of San Diego is a specific patch of water. Missing it by even a few miles could complicate the recovery operation. The burns must be exact. The crew tests compression garments designed to help their cardiovascular systems handle the G-forces of re-entry. After 10 days in microgravity, the human body has begun adapting to weightlessness. Blood has redistributed from the legs toward the head. The heart has slightly atrophied. Blood pressure regulation has shifted. When the G-forces of re-entry hit, blood will rush from the brain toward the feet. Without countermeasures, an astronaut who has been in microgravity for 10 days could experience lightheadedness, tunnel vision, or even loss of consciousness during the most critical phase of the entire mission. The compression garments work like the G-suits worn by fighter pilots. They squeeze the legs and abdomen, preventing blood from pooling in the lower body. The crew practices donning them. They rehearse the choreography of re-entry. Every step is scripted. Every action has been practiced in simulators hundreds of times. But simulators do not replicate the feeling of knowing that the heat shield beneath your seat is the same basic design that cracked apart 3.5 years ago. Day 9 is the last full day in space. The crew studies re-entry procedures one final time. They review abort scenarios. They check their suit integrity. They test their communications links. They prepare the cabin for the violence of atmospheric entry, stowing loose equipment, securing anything that could become a projectile under 5 or 6 G-forces. Commander Wiseman and Pilot Glover review the hand controller procedures for re-entry. Although Orion's re-entry is primarily automated, the crew has the ability to take manual control if the computers fail. In that scenario, Glover would hand-fly the capsule through the atmosphere, adjusting the angle of attack to manage heating and G-forces while targeting the splashdown zone. It is a scenario no one wants to execute. But they prepare for it anyway because preparation is what separates survival from catastrophe. The emotional arc of the mission has shifted completely. The first half was defined by wonder, the launch, the far side, the distance record, the Earthrise. The second half is defined by anticipation. Every hour that passes brings them closer to the atmosphere. Every system check is one step closer to the moment when physics takes over and engineering either holds or fails. The crew sleeps their last night in space, floating in their wall-mounted sleeping bags. The Earth visible through the windows, larger now, filling more of the frame with each passing hour, blue and white and impossibly beautiful against the black. When they wake up, it will be day 10, the final day. The day the service module separates, the day the heat shield faces the atmosphere, the day 5,000-degree plasma engulfs the capsule, the day the parachutes either open or do not, the day they come home or do not come home. 9 days, 685,000 miles. They have seen the far side of the moon, broken the distance record, and survived the radiation of deep space. Now there is only one thing left, and it is the thing that might kill them. In less than 10 minutes, they will hit Earth's atmosphere at 25,000 miles per hour. The temperature outside their window will reach 5,000 degrees, and the heat shield holding back that inferno is the same design that cracked apart on Artemis I. Everything the documentary has been building toward comes down to this. Chapter 11, 25,000 miles per hour. Day 10 begins with separation. High above the Pacific Ocean, the Orion crew module detaches from the European-built service module that has kept it alive for the past 10 days. Explosive bolts fire. Mechanical latches release. The two halves of the spacecraft drift apart. The service module, with its solar arrays and engine and propellant tanks, tumbles away. It will burn up in the atmosphere. It is designed to be destroyed. It has served its purpose. The crew module is now alone, a blunt cone of metal and heat shield falling toward the Earth under ever-increasing gravitational acceleration. The 4 astronauts are strapped into their seats. They are wearing their Orion crew survival system suits, the orange pressure garments that will protect them if the cabin depressurizes. Their visors are down. Their gloves are locked. Their harnesses are tight. The reaction control thrusters fire in short, precise bursts, orienting the capsule so that the heat shield faces the direction of travel. The blunt end forward. The ablative barrier between the crew and the atmosphere aimed directly into the path of re-entry. This is it, the moment the entire mission has been building toward since Chapter 1. The heat shield that cracked on Artemis I is about to be tested again, this time with 4 human beings sitting on top of it. Orion is falling toward Earth at approximately 25,000 miles per hour. That is 7 miles per second, roughly 33 times the speed of sound. It is the fastest crewed atmospheric re-entry ever attempted, exceeding even the speeds achieved by Apollo capsules returning from the Moon, because Orion is heavier and its trajectory is steeper. At approximately 75 miles above the Pacific Ocean, the capsule hits the discernible atmosphere. The air molecules at this altitude are sparse, thin, almost nothing. But at 25,000 miles per hour, almost nothing becomes everything. The capsule compresses the air ahead of it so violently that the gas molecules cannot move out of the way fast enough. They pile up, they compress, they heat. A shock wave forms around the capsule, a boundary of superheated plasma that engulfs the entire vehicle. The external temperature climbs, 1,000 degrees Fahrenheit, 2,000, 3,000, 4,000, 5,000. Half the temperature of the surface of the sun. The plasma glows orange, then white, then a blinding, incandescent fury that turns the windows into walls of light. From outside, the capsule is a streak of fire across the Pacific sky. A man-made meteor plunging toward the ocean. Inside the capsule, the temperature is controlled. The heat shield is doing its job. The avcoat material is charring and ablating, carrying thermal energy away from the spacecraft as it burns. This is the design. The material is supposed to sacrifice itself, layer by layer, so that the structure behind it stays cool enough to survive. On Artemis I, the material did not behave as designed. It cracked. It ejected in chunks. It left gouges and holes that exposed deeper layers to temperatures they were never meant to endure. For Artemis II, NASA changed the trajectory. No skip re-entry. No bouncing off the atmosphere and re-entering a second time. Instead, a direct plunge. Steeper, more intense. Higher G-forces on the crew, but a single continuous heating profile. No heating and cooling cycles. No time for gases to build up inside the avcoat blocks. No opportunity for the conditions that caused the Artemis I failure. The crew is experiencing roughly 5 to 6 times the force of gravity. 5 to 6 G means that each astronaut feels as though they weigh 5 to 6 times their normal body weight. Their arms are heavy. Their heads are pressed back into the seats. Breathing requires effort. The compression garments around their legs and abdomen are squeezing, keeping blood from pooling in their lower bodies, keeping their brains supplied with oxygen. This is what fighter pilots train for. And 3 of the 4 people aboard Orion are fighter pilots. Then comes the blackout. For approximately 5 minutes, the electrically charged plasma surrounding the capsule blocks all radio communication. Mission control in Houston goes silent. The telemetry screens freeze on the last received data. The flight controllers sit at their consoles and wait. There is nothing they can do, no commands they can send, no adjustments they can make. The crew is alone with physics. This is the longest 5 minutes in the history of any mission control. Every person in that room knows the heat shield's history. Every person knows what Kamada said. Every person has seen the photographs from Artemis I. And every person is staring at a screen that has gone dark and waiting for it to come back to life. Inside the capsule, the crew can see the plasma through the windows. They can feel the deceleration pressing them into their seats. They can hear the rumble and roar of atmospheric friction transmitted through the structure. The capsule is shaking. The heat shield is working or it is failing, and there is no way to know which until the temperature gauges on the interior structure tell the story. Danny Oliva said it before the mission. Will the heat shield crack? Yes, it is going to crack. The question is whether it cracks enough to compromise the thermal protection, whether the ablation is controlled or catastrophic, whether the chunks that come off are small enough to maintain the shield's integrity or large enough to expose the structure beneath. Steve Scotty at NASA Langley Research Center described the fundamental challenge. The material itself changes every 20 seconds or so during re-entry. The models cannot fully capture a substance that is transforming in real time. It chars, it off-gasses, it ablates, it cracks, it restructures at the molecular level, all while being subjected to temperatures that would melt steel and pressures that would crush concrete. The seconds pass. The plasma begins to thin. The orange glow outside the windows fades. The G-forces ease. The capsule is slowing. It has passed through the worst of the heating. The temperature outside is dropping. The atmosphere is thickening. Drag is bleeding off velocity. Radio contact is restored. Mission Control hears a voice. The telemetry screens flicker back to life. Data flows. The capsule is intact. The heat shield held. The crew is alive, but they are not home yet. At approximately 36,000 feet above the Pacific Ocean, the parachute sequence begins. It is the most complex parachute system ever flown on a piloted spacecraft. 3 small parachutes deploy first, pulling a protective cover from the main chute storage bay. 2 23-foot drogue chutes unfurl at 24,000 feet, stabilizing the capsule and slowing it to about 307 miles per hour. 3 pilot chutes deploy at 9,500 feet, pulling out 3 main parachutes, each 116 feet in diameter. These enormous canopies inflate in stages between 8,000 and 4,000 feet. The speed drops from 300 miles per hour to just 17 miles per hour. 5 airbags inflate around the top of the capsule to ensure it lands upright regardless of how it hits the water. And then, splashdown. The capsule hits the Pacific Ocean, approximately 50 miles off the coast of San Diego. The date is April 10th, 2026. 10 days after launch, 685,000 miles after leaving Kennedy Space Center, the most dangerous trip home in the history of human spaceflight is over. But the mission is not complete. Not yet. A Navy recovery team is waiting on the water, and the first thing they need to examine is the heat shield. Chapter 12. Recovery. The Orion capsule bobs in the Pacific Ocean. Its white exterior is scorched and blackened from re-entry. The 5 airbags around the upper ring keep it floating upright, the hatch above the waterline. Inside, 4 astronauts are alive. They have been in space for 10 days. Their muscles have begun adapting to weightlessness. Their cardiovascular systems have recalibrated for a world without gravity. And now, gravity is back. Every movement feels heavy. Their heads feel strange. The fluid that has been floating freely in their bodies for the past week and a half is rushing back toward their feet. Earth feels like it weighs more than they remember. The recovery operation has been in motion for days. More than 100 NASA and contractor personnel, along with United States Navy support, deployed from Naval Base San Diego approximately 3 to 4 days before the expected splashdown. They positioned at a midway point in the Pacific and moved to the splashdown coordinates within 24 hours of the capsule hitting the water. An elite team of Navy divers enters the water first. They approach the capsule in rigid, inflatable boats. Their job is to assess the exterior, check for leaking chemicals, check for hot spots from re-entry, verify that the capsule is stable and safe to approach. The heat shield is still hot. The exterior surfaces may be off-gassing. Toxic hydrazine residue from the reaction control thrusters could be present. The divers are trained for all of this. Once the capsule is deemed safe, a tow line is attached. The capsule is pulled toward a San Antonio-class amphibious transport dock, a large Navy vessel with a well deck that can be flooded to allow the capsule to float inside. The ship's deck is then pumped dry, and the capsule rests on a cradle. Only then are the astronauts extracted. The hatch opens. Fresh air rushes in. After 10 days of recycled atmosphere inside a sealed capsule, the Pacific breeze must feel like a revelation. The crew is helped out carefully. After extended time in microgravity, standing upright is disorienting. Balance is compromised. Muscles that have not supported body weight in over a week protest. The astronauts may need assistance walking. Medical teams are standing by to assess their condition. NASA recovery engineer Melissa Seiler described the philosophy simply: the mission is not complete until we ensure the safety and the return of the crew back home. But while the medical teams attend to the crew, the engineers are focused on something else entirely. The heat shield. The bottom of the Orion capsule is the first thing the recovery team examines in detail. How did the avcoat perform with the direct re-entry profile? Did it crack? How much material was lost? Are the gouges similar to Artemis I or different? Is the pattern consistent with NASA's models, or does it show unexpected behavior? This data is not academic. It will determine the future of the entire Artemis program. If the direct re-entry profile performed as predicted, if the heat shield cracked in manageable ways and maintained its thermal protection throughout, then NASA's gamble is validated. The decision to fly without an unmanned test is retroactively justified. The program moves forward. If the heat shield performed worse than expected, if the damage approaches or exceeds what was seen on Artemis I, despite the changed trajectory, then the program faces a crisis. Every future Artemis mission uses the same basic heat shield design. Artemis III, the planned rendezvous and docking test in low Earth orbit, would need to be re-evaluated. Artemis IV, targeted as the first crewed lunar landing since Apollo 17, could be delayed by years. NASA has already announced a new heat shield design for Artemis III with modified block density and improved gas venting to address the issues discovered on Artemis I. But Artemis III's heat shield will not face lunar return speeds. It is a low Earth orbit mission. The first real test of the redesigned heat shield at full lunar return velocity will not come until Artemis IV, currently targeted for 2028. The post-flight inspection of the Artemis II heat shield will take weeks. Engineers will photograph every square inch of the surface. They will measure the depth of every gouge. They will analyze the pattern of ablation and compare it to the computational models. They will look for evidence of gas buildup, cracking, and material ejection. They will determine whether the direct re-entry profile eliminated the failure mode or merely reduced its severity. Charles Kamada will be watching. Danny Olivas will be watching. Every heat shield engineer in the aerospace industry will be watching. The photographs from the Artemis II heat shield will be the most scrutinized images in the history of thermal protection systems. Beyond the heat shield, the Artemis II mission opens the door to everything that comes next. NASA Administrator Jared Isaacman has restructured the program aggressively. Artemis III, originally planned as the first lunar landing, has been redesigned as a near-Earth orbit mission to test rendezvous and docking with a lunar lander. This is a significant change. It adds an additional mission between Artemis II and the actual landing, providing more test data but also consuming time and budget. Artemis IV is now targeted as the first crewed lunar landing since 1972. It will use a SpaceX Starship-derived human landing system to carry astronauts from lunar orbit to the surface. The mission profile is complex. Orion will fly to lunar vicinity. The Starship lander will be pre-positioned in lunar orbit after multiple refueling flights. The crew will transfer from Orion to Starship, descend to the surface, explore, and then return to Orion for the journey home. Annual landings are planned thereafter. The goal is not flags and footprints. It is sustained human presence, a base at the lunar South Pole, mining, water ice, manufacturing rocket fuel, growing food in lunar regolith, testing the technologies and procedures that will eventually carry humans to Mars. The $20 billion moon base that Isaacman announced represents the most ambitious construction project ever attempted off Earth. It will be the most isolated human settlement in history. Resupply from Earth takes 3 days minimum. Medical evacuation is measured in days, not hours. The crew will need to be self-sufficient to a degree that no space mission has ever required. Every lesson learned on Artemis II feeds into this vision: the radiation data, the life support performance, the heat shield behavior, the human factors of living in a cramped spacecraft for extended periods. The crew of Artemis II are not just astronauts, they are test subjects. Their bodies and their experiences are the data that will determine whether humanity can survive and work beyond low Earth orbit for extended periods. The splashdown is a beginning, not an ending. The capsule is recovered, the crew is safe, the heat shield is examined, and the program moves forward into a future that is simultaneously thrilling and uncertain. Because the next mission will be harder, the one after that will be harder still. And at the end of the road, if everything works, human beings will stand on the moon again for the first time in more than half a century. But before we look forward, we need to look back, to the launch pad, to the history that haunts it, and to the ghosts that walked the same path. These 4 astronauts walked on April 1st, 2026. Chapter 13. Pad 39B. A History of Fire. Launch Complex 39B is a 344-acre site on the eastern shore of Merritt Island, Florida. It is a patch of flat coastal land surrounded by sawgrass and saltwater, battered by hurricanes and bleached by the subtropical sun. From a distance, it looks industrial, unremarkable. A collection of concrete structures and steel towers and service roads leading to a raised platform where rockets stand before they fly. But this patch of ground has witnessed more history than almost any other place on Earth. 60 launches have departed from Pad 39B. The first was Apollo 10 in May of 1969. That mission was the dress rehearsal for the first moon landing. Astronauts Thomas Stafford, John Young, and Eugene Cernan flew their lunar module to within 9 miles of the lunar surface, tested every system, verified every procedure, and then came home so that Apollo 11 could go 2 months later and land. Pad 39B made the moon landing possible. 3 Skylab missions launched from this pad in 1973 and 1974, carrying crews to America's first space station. The Apollo-Soyuz test project launched from here in 1975, the first international docking mission between American and Soviet spacecraft. And then came the shuttle. 53 space shuttle missions launched from Pad 39B over 3 decades. Discovery, Atlantis, Columbia, Challenger. The shuttle fleet launched from both Pad 39A and 39B, but 39B holds a particular weight in the memory of the space program, because it was from this pad, on January 28, 1986, that the Space Shuttle Challenger launched for the last time. The morning was cold, unusually cold for Florida. Temperatures at the pad had dropped to 36 degrees Fahrenheit overnight, well below the qualification range for the solid rocket booster. O-ring seals. Engineers at Morton Thiokol, the company that built the boosters, had raised concerns the night before. They warned that the O-rings might not seal properly in the cold. They recommended delaying the launch until temperatures rose. NASA management pushed back. The mission had already been delayed multiple times. The agency was under pressure to maintain its launch schedule. The concerns were discussed. The engineers were overruled. The launch proceeded. 73 seconds after liftoff, hot combustion gases burned through the failed O-ring on the right solid rocket booster. The flame impinged on the external tank. The tank ruptured. The shuttle broke apart at 48,000 feet. 7 crew members died. Krista McAuliffe, who would have been the first teacher in space, died with them. The nation watched it happen on live television. The investigation that followed, led by physicist Richard Feynman and former Secretary of State William Rogers, revealed a pattern that would echo through NASA's history for decades. Engineering concerns raised and dismissed. Schedule pressure overriding safety culture. Management convinced that past success guaranteed future safety. The O-rings had shown damage on previous cold weather launches. The warnings were in the data. They were ignored. 17 years later, the pattern repeated. On February 1, 2003, the Space Shuttle Columbia broke apart during re-entry over Texas and Louisiana. 7 crew members died. The cause was a piece of insulation foam that had broken off the external tank during launch, 81 seconds after liftoff. The foam struck the leading edge of the left wing, puncturing the reinforced carbon thermal protection panels. During re-entry, superheated plasma entered the wing through the breach. The wing failed. The shuttle disintegrated. Engineers had noticed the foam strike during the mission. They raised concerns. They requested satellite imagery of the wing to assess potential damage. The request was denied by mission management. The official reasoning was that nothing could be done even if damage was confirmed. The shuttle had no ability to repair its heat shield in orbit. So the concern was filed and forgotten. 14 days later, 7 people were dead. The Columbia Accident Investigation Board found the same institutional dynamics that had been identified after Challenger. Schedule pressure. Normalization of deviance, a term meaning that known problems are gradually accepted as routine because they have not yet caused a catastrophe. Management structures that filtered bad news before it could reach decision makers. A culture that rewarded optimism and penalized dissent. Charles Kamada flew on the first shuttle mission after Columbia. Discovery, STS-114, in 2005. He was selected specifically because of his expertise in thermal protection systems. He later led the engineering investigation into Columbia's root cause. He spent years studying exactly how institutional dysfunction could kill astronauts who were relying on heat shields. And then he watched it happen again. Not the disaster, the pattern. The institutional behavior, the motivated reasoning, the dismissal of dissent. When the Artemis I heat shield came back damaged, Kamada saw the same dynamics at work. Engineering concerns, raised and acknowledged, but not acted upon. Schedule pressure, driving decisions that should be driven by data. Computational models used to justify conclusions that the models themselves could not reliably support. Dissenting voices, invited to participate, and then marginalized when their conclusions were inconvenient. Kamada posted publicly about his frustration. "Wake up, NASA," he wrote. "My book exposed the corruption post-Columbia. Now the corruption and dysfunction are being exposed during Artemis. Do not let Artemis II become another Columbia. The comparison is pointed and deliberate." Kamada is not a crank. He is not a conspiracy theorist. He is a former NASA astronaut with a doctorate in engineering who flew on the most dangerous shuttle mission in history and then spent years studying why Columbia was lost. When he draws a parallel between Columbia's institutional failures and the Artemis II heat shield decision, the comparison carries weight. NASA disputes the characterization. Laurie Glaze, the acting associate administrator for Exploration Systems Development, told reporters at the Flight Readiness Review that the discussions were extremely thorough, open, and transparent. She said the agency talked extensively about risk posture and mitigation. The review produced a unanimous go vote. But unanimity in a room full of people who have spent years working toward a launch date is not the same as consensus among all qualified experts. The people who said no were not in that room. They were outside it, talking to reporters, posting on social media, and hoping they were wrong. The uncomfortable question that haunts Pad 39B is simple. Should Artemis II have flown unmanned first? NASA could have repeated the Artemis I mission with the new direct re-entry trajectory. They could have validated the heat shield fix without risking 4 human lives. The data would have been definitive. The cost would have been another $4 billion and another 2 years of delay. They chose not to. The reasons were complex. Schedule pressure from a program that was already years behind. Budget pressure from an agency that was already billions over budget. Political pressure from an administration that wanted a crewed moon mission on its watch. And the genuine engineering judgment of the majority of NASA's workforce that the heat shield would hold. Whether that judgment was correct will be determined by the post-flight inspection. If the heat shield performed well, the decision is vindicated. If it did not, the decision will be examined under the harshest light imaginable, and the ghosts of Challenger and Columbia will be invoked again. Pad 39B does not forget its dead. The ground remembers every vibration. The steel remembers every flame, and the people who work there carry the weight of knowing that this pad has seen both the greatest triumphs and the greatest tragedies in the history of American spaceflight. The crew of Artemis II walked the same walkway that Challenger crew walked 40 years ago. They rode the same elevator. They entered the same white room. They signed the same wall. And they climbed into a spacecraft with a heat shield that some of the smartest people in aerospace said should not carry a crew. The question is whether courage and engineering judgment will be proven right, or whether the pattern will repeat one more time. There is one question left, the deepest one, the one that sits beneath all the engineering and politics and history. Why do we keep doing this? Why do we keep sending people into the void? Chapter 14. Why we go. Between December of 1972 and April of 2026, no human being left low Earth orbit. 53 years. An entire generation was born, grew up, grew old, and in some cases, died without anyone going to the moon. The International Space Station was extraordinary. It represented 20 years of continuous human presence in space. But the station orbits at 250 miles. The moon is 250,000 miles. The difference is not incremental. It is civilizational. Every single member of the Artemis II crew was born after Apollo 17. Reed Wiseman, Victor Glover, Christina Koch, Jeremy Hansen. None of them had ever been to deep space. None of their trainers had been to the moon. The knowledge of how to send human beings beyond low Earth orbit and bring them home had to be rebuilt from institutional memory, archived documents, retirement interviews with Apollo-era engineers, and new engineering developed from scratch. Think about what that means. An entire body of operational knowledge, the kind that only comes from doing something, not studying it, was allowed to atrophy for half a century. We knew how to go to the moon in 1972. By 2026, we had to learn how all over again. The Artemis program is not just a space mission. It is a civilizational memory recovery project. The official justification for returning to the moon is practical. NASA frames Artemis as a stepping stone to Mars. The moon is 3 days away. Mars is 7 months. You test life support systems on the moon. You test radiation shielding. You test habitat construction and resource extraction and human endurance in an environment where rescue is possible before you commit to a destination where rescue is not. If something goes wrong on the Moon, you can come home in 3 days. If something goes wrong on Mars, you are on your own for the better part of a year. The South Pole Base will be the most isolated human settlement ever attempted, mining water ice from permanently shadowed craters, producing oxygen through electrolysis, manufacturing hydrogen and oxygen rocket fuel from lunar resources, growing food in regolith that has never known rain. Every lesson learned there applies to Mars. Every system tested there reduces the risk of a Mars mission by some measurable amount. This is the rational argument. It is sound, it is persuasive, and it is incomplete. Because the rational argument does not explain why 4 people climbed aboard a machine with a cracked heat shield and rode 8.8 million pounds of thrust into the sky. Rationality does not explain that. Something else does. Every Apollo astronaut who saw Earth from the Moon described a profound shift in perspective. They called it the overview effect. The planet appears fragile from that distance, borderless, singular, a blue marble hanging in infinite blackness with a tissue-thin atmosphere that is the only thing separating life from the void. Michael Collins, who orbited the Moon alone while Armstrong and Aldrin walked on the surface, called Earth a tiny, fragile-looking ball. Edgar Mitchell described an explosion of awareness, an understanding that hit him not in his mind, but in his body, that everything is connected, that the boundaries humans draw on maps are fictions, that the planet is one system and we are part of it. The crew of Artemis II will see this. 4 new human beings will look back at Earth from the far side of the Moon. And for the first time in history, those eyes will include a woman, a person of color, and someone who is not American. Koch and Glover and Hansen will bring perspectives that the all-white, all-male, all-American crews of Apollo could not. What will they see? What will they feel? What will they tell us about ourselves when they come home? Christina Koch tried to articulate it before the mission. She asked people to think about what it means to be among the humans who can call the Moon a destination. Not something you look at, not a light in the sky, a place you go, a place you travel to, a place that is part of your world in the same way that a city on the other side of the ocean is part of your world. Distant, difficult to reach, but real, tangible, reachable. There is something in the human species that will not stop reaching. It is not rational. It is not practical. It is the same impulse that drove the first humans to cross the land bridge into the Americas. The same impulse that built boats to cross oceans when staying on shore was safer. The same impulse that climbed mountains that did not need to be climbed and mapped rivers that did not need to be mapped and asked questions that did not need to be asked. Artemis II is a test flight. Nobody landed. Nobody planted a flag. Nobody collected rocks or set up experiments on the surface. 4 human beings flew to the Moon and came home. That is all. And that is everything. Because the test flight is not the point. The point is what it proves. It proves that after 53 years of silence, humanity can still do this. It proves that the knowledge can be rebuilt. It proves that the heat shield, for all its controversy, can be managed. It proves that the radiation can be endured. It proves that 4 people can live in a capsule the size of 2 minivans for 10 days and perform their jobs and maintain their focus and bring the spacecraft home. It proves that we can go back. And going back is the first step to going farther. The Moon is not the destination. Mars is not the destination. The destination is everywhere. The destination is every place we have not yet been, every question we have not yet answered, every horizon we have not yet crossed. The Moon is just the next step, the stepping stone, the proving ground for a species that has spent its entire existence on one small planet and is now, tentatively, clumsily, expensively, bravely, reaching for the next one. The $93 billion is real. The heat shield controversy is real. The institutional dysfunction is real. The political gamesmanship is real. The cost-plus contracts, and the congressional pork, and the schedule delays, and the budget overruns are all real, and none of them change the fundamental truth of what happened on April 1st, 2026. 4 people chose to go. They knew the risks. They understood the odds. They had read the dissenting reports and the safety analyses and the comparisons to Challenger and Columbia. They looked at all of it, and they walked to the launch pad anyway. They signed the wall of the White Room. They strapped into their seats. They felt 8.8 million pounds of force push them off the surface of the Earth and into the sky. They saw the far side of the Moon. They broke the distance record. They looked back at Earth from 250,000 miles away and saw what only a handful of human beings have ever seen. A planet so beautiful and so fragile that the sight of it from that distance changes you forever. Reed Wiseman said it simply before the mission. The 4 of us, we are ready to go. The team is ready to go. The vehicle is ready to go. Ready to go. 3 words that carry the weight of 53 years of waiting. 3 words that carry the ambitions of a species that cannot stop exploring. 3 words that carry the risk, and the wonder, and the terror, and the beauty of leaving everything you know behind and heading into the dark. Artemis II is not the end of the story. It is the first sentence of a new chapter, a chapter that will include lunar bases and Mars missions and technologies we have not yet invented, and discoveries we cannot yet imagine. A chapter that will be written by people who are alive today, people who watched this launch, people who felt the ground shake when 8.8 million pounds of thrust pushed a 322-foot rocket off the pad and into the Florida sky. The Moon is 250,000 miles away. It has been there for 4.5 billion years. It will be there for billions more, patient, silent, waiting. And now, for the first time in half a century, we are going back. If you enjoyed this deep journey into the Artemis II mission, the science of deep space travel, and the story of the 4 people brave enough to go, please like this video and subscribe to the channel. Your support makes these detailed investigations possible. Tell us in the comments, would you go? If you knew the heat shield had cracked before, if you knew the odds, if you knew everything the crew of Artemis II knew, would you climb aboard? And what do you think we will find when we finally land on the Moon again? These are not just questions for astronauts. They are questions for all of us, because the Moon is not going anywhere, but we are. Thank you for watching. We will see you in the next investigation.